We've already built 2 of the 3 conservation laws on this little cube. Mass, how much fluid is there? Momentum, how it pushes and speeds up. Today, the third and last one, energy, heat, and temperature. Same cube, and this time the rule is the first law of thermodynamics. Here's the plan. On the same cube, we derive the energy equation straight from the first law of thermodynamics. We track the energy in and out, and along the way, we'll finally explain what those 2 compact symbols, the divergence and the Laplacian, actually mean. First, the energy inside the cube. We track all of it, the heat energy, how fast the molecules jiggle, plus the energy of the fluid's motion. Together, that's the total energy. Per unit volume, it's the density times that energy, times the cube's volume, the energy stored in the box. Why count the motion as well? Because the forces are about to do work on the moving fluid, shuffling energy between motion and heat, and we'll drop the tiny motion part right at the end. The first law is just energy bookkeeping. Energy can't appear or vanish, only move or convert. So the energy in our box changes for a few reasons. Energy carried in and out by the flow, heat conducted in and out, the work the forces do on the fluid, and any heat added. The new players, compared to momentum, are conduction and work. Start with the flow carrying energy. Same as before, energy rides in through the left face and out through the right. We label the left face position X and the right one box width further along. Their difference, and because the cube is infinitely small, is exactly a derivative. Do that on all 3 pairs of faces, and you get 3 terms, how the energy flow changes along X, along Y, and along Z. And here's that first compact symbol. That whole sum is written as the divergence of the energy flow. That's all the divergence means. Add up how the flow changes in each direction, the net energy leaving the point. Now, heat conduction. And this one needs no flow at all. Heat moves on its own from hot to cold down the temperature gradient. Fourier's law makes it precise. The heat flux is the conductivity times how steeply the temperature drops. Put that heat flux on the faces, in one side, out the other. The difference, with the cube infinitely small, is a derivative again, but the flux is itself a gradient of temperature, so a derivative of a gradient gives a second derivative, the temperature's curvature. Do it on all 3 pairs, and the 3 second derivatives add up to the second compact symbol, the Laplacian of temperature. The Laplacian just means the sum of the curvatures, how sharply the temperature bends, the net heat conducting into the point. Now the work done by the forces, starting with pressure. Pressure pushes on the face with a force. Pressure times area, and the fluid moves through it. Force times velocity is power, so the pressure does work at the rate pressure times velocity times the area. Sum it across the faces, in one side, out the other. And because the cube is infinitely small, the pressure work becomes minus the divergence of pressure times velocity. We keep it as its own term, right there in the equation. Friction does work too. Remember the shear stress from the momentum video, the viscosity times how fast the velocity changes between layers. It acts along the face, and the face is moving, so it also does work. Stress times velocity times the area. Sum across the faces, and because the cube is infinitely small, the friction work becomes the divergence of the stress times velocity. By the product rule, it splits in 2. One part speeds the flow up, the other is the dissipation. And because it's a square, it's always positive. Friction can only heat the fluid, never cool it. And gravity. Gravity is the body force from the momentum video as the fluid falls or rises. That force does work too. Simply the force, dotted with the velocity, acting on all the mass. No faces this time, it's a body force. That leaves one term we don't derive, a heat source. A source can be anything, a chemical reaction, a heater, absorbed light. Everything else we build from the cube, the source, we just keep general. Now put every block together and divide by the volume. The energy stored, plus what the flow carries, equals the pressure work, plus conduction, plus friction, plus gravity, plus the source. Every term we derived from the cube, only the source stays general. That's the energy equation. One last move. For a slow flow, the motion energy is tiny, so we drop it. The convection and the pressure work then combine into what's called enthalpy transport, and the heat content becomes the heat capacity times temperature. The left side collapses to density times heat capacity times the rate the temperature changes following the flow. And that, including the pressure work, is exactly why the temperature equation carries the constant pressure heat capacity, not the constant volume 1. The friction heat stays. In plain temperature, here's what it says. Heat is carried along by the flow. Convection, it spreads out by conduction, diffusion, and friction adds a little heat of its own. Switch the flow off, and you're left with the famous heat equation, temperature smoothing itself out over time. So that completes the set. Mass, momentum, and energy. 3 conservation laws, all on one tiny cube. That's the heart of CFD. Everything a solver does is these 3 laws on millions of little boxes. See you in the next one.